Burn like a pro.
Have you ever stared at your electricity bill and just wondered what you're really paying for? I mean, it's so much more than just a number on a page. It's actually the final chapter of this incredible story that starts in the invisible world of colliding electrons and ends, yep, right in your wallet. So today, we're going to trace that exact journey, starting right at the very beginning. Let's dive in. To really get a grip on electrical power, we have to think small, like impossibly small. We're about to go deep inside a copper wire to see this invisible friction that powers, well, basically everything you own. Okay, so this is what's happening on that microscopic level. You see, electrons don't just get a free pass to slide through a wire. No, they're constantly crashing into the atoms of the conductor itself. And every single one of those billions upon billions of collisions transfers a tiny bit of energy, making the atoms vibrate like crazy. And all that vibration, well, that's heat. Simple as that. And that microscopic traffic jam, it actually has a name: electrical resistance. It's this fundamental property that every material has that kind of pushes back against the flow of electricity. Think of it like electrical friction. But here's the kicker. This isn't some flaw or just wasted energy. It's the central mechanism that we're about to put to work. So, we've seen the action, right? But how in the world do we measure it? How do we control it? To do that, we need to learn the language of power. So, let's build ourselves a little dashboard to make sense of it all. Here are the two main dials on our dashboard. The first one, P equals E over T, is pretty straightforward. It just tells us that power is the rate at which we're using energy. How fast is it happening? But the second one, P equals V times I, is maybe even more useful. It says power is a product of voltage, think of that as the electrical pressure, and the current, which is the flow. These are the two key ways we can measure what's going on in any circuit. And the standard unit for all of this is the watt. Now, a watt is built on an even smaller unit of energy called the joule. Just imagine a joule as one tiny little packet of energy. It's roughly what it takes to lift an apple about 3 feet off the ground. So a watt is a rate. 1 watt means one of those joules is being used up every single second. So a 100-watt light bulb, it's burning through 100 joules of electrical energy, turning it into light and heat every second it's on. Now let's see this in action, because this is where it gets interesting. Look at this comparison between a regular light bulb and a big heating element. The bulb, right, it sips electricity, using just 30,000 joules in 5 minutes. But the heating element, whoa, it pulls way more current and chews through a staggering 900,000 joules in the exact same amount of time. That's 30 times more energy. It really shows you the massive difference in power these devices demand. Now, all this talk about heat from resistance, it kind of sounds like a bad thing, right? Like wasted energy. But what if? What if we could take that problem, that friction, and make it the entire point of an appliance? What if we could turn that friction into function? And that is exactly what we do. Devices like this electric kettle are, believe it or not, masterpieces of intentional inefficiency. That coil at the bottom isn't designed to let electricity flow easily. It's engineered to fight it, to create a huge traffic jam, maximizing those collisions we saw to generate an incredible amount of heat, all on purpose. You know, the recipe is just brilliant in its simplicity. You pick a material with super high resistance to create a ton of heat, and then you just make sure it has a really high melting point so it doesn't, destroy itself. And that's it. That's the basic technology behind our kettles, our ovens, our space heaters. We've literally turned a law of physics into a super reliable household tool. Okay, so we've bridged the gap from the microscopic world of atoms to the appliances sitting in our kitchen. Now it's time for the final and maybe most important leg of our journey, connecting the physics of power to the price we all pay. It's time to go from watts to our wallets. But this brings up a whole new problem. Remember that heating element that used almost 1 million joules in just 5 minutes? Can you imagine if our utility bills were calculated in joules? The numbers would be ridiculously huge, totally impractical. So how do the power companies get around this? They solve it with a much bigger, much friendlier unit of energy, the kilowatt hour. It's so elegant. Instead of counting all those tiny joules one by one, we just bundle them up into a single manageable block. A kilowatt hour is just the total energy used by a 1,000-watt appliance if you leave it running for 1 full hour. It's a perfect solution to a very big numbers problem. And using this unit gives us this super simple 2-step formula that every utility company on the planet uses. First, you figure out the total energy you used by multiplying the power in kilowatts by the time in hours. Then, second, you just take that number and multiply it by whatever the cost per unit is. That's it. That's the entire math behind your bill. So let's run the numbers with a quick example. Let's say we've got a 1,000-watt electric heater. That's easy. It's 1 kilowatt. If we run it for 3 hours, the math is about as simple as it gets. 1 kilowatt times 3 hours equals 3 kilowatt hours of energy used. And now for the final step. Let's say your power costs 20 cents per kilowatt hour. We just multiply our 3 kilowatt hours by 20 cents, and there you have it. The real, tangible cost to run that heater for 3 hours is 60 cents. And just like that, the entire circuit is complete. We started at the micro level with the physical collision of electrons creating heat. Then we found a way to quantify it all with math. We saw how that power gets harnessed in our homes. And finally, we landed at the macro level of economics, where all that microscopic work gets bundled, priced, and delivered to you as one single number on a bill. From the electron to the economy, all one seamless process. So the next time you open up your utility bill, I hope you don't just see a number. I hope you see the story behind it. Because every single cent on that bill, it's a record of billions and billions of microscopic collisions, all doing work just for you.